Now, let's look at how we can derive the Black-Scholes formula for computing the price of either a European call option or a European put option using the risk neutral valuation model. Whenever I say risk neutral, what is that? We are looking at, whenever we are talking about a risk neutral pricing or risk neutral valuation, we are looking at discounting the expected future payoffs. Expected future payoffs that are going to come on maturity. That is what, when I am discounting them to the present value, that is what we call as a risk neutral valuation. And here, especially with respect to this option pricing, we go under the assumption that the asset prices follow a log normal distribution, which means the logarithm of the asset prices is going to follow the normal distribution, which means if at all I want to look at the value of the option, we are looking at, okay, what is the expected value or expected payoff at time t, and I am taking the discounting of it, so I am doing it e to the power of minus rt. So this is what will give me the value of the option based on a risk neutral valuation model. And we have already established the typical fact, the log normal model for the asset prices. We have established the equation saying log S2 by S1, which is the logarithms of the returns. We have already established that it can be modeled in the form of mu minus q minus sigma squared by 2 into t, which is the difference in the time periods between S2 and S1, plus sigma times the square root of T2 minus T1 times standard normal variable Z. Now, the same application is what I am going to use even now under the assumption that mu I am taking it as some r, and T2 minus T1 I'll take it as T minus 0, which means T2 I take as T, T1 I take as 0, which means T period to maturity. Whatever I'm talking of, I have T period to maturity. So I'm taking it as 0, T1 I'm taking as 0, T2 I'm taking as capital T, which means the same formula logarithm S2 by S1 will become r minus q minus sigma squared by 2 times t plus sigma root t times z. So that is the kind of an equation I am going to use. And here also, because I have made T2 and T1 already, so I can call this as ST divided by S0. So that is the first equation I am going to get, log ST divided by S0. I'll make it as R minus Q minus sigma squared by 2 into T plus sigma root T times Z. So from here I can simplify. I'll take out the log. St by S naught will become e to the power of R minus Q minus sigma squared by 2 times T plus sigma root T times Z. So from there I get St is coming out as S0 times e to the power R minus Q minus sigma squared by 2 times T plus sigma root T times Z. So this is what is an expression for St. So now let's say I want to do the price determination for a European call option. Now what is the payoff? See, if I am going with a risk neutral pricing model, The payoff for a European call option is typically the maximum. First, let me look at the payoff. Maximum of ST minus K, comma 0. This is what is the payoff, and I'll take the present value of that. That is what should be the price, right? The expected value of the maximum of ST minus K, comma 0 times e to the power of minus RT. That is the price of the call option. The same way, probably if I am looking at the price of the put option, e to the power of minus RT times the expected value of maximum of K minus ST, comma 0. So now what we will try to see is, first let me work it out for the call option. So I need to know maximum of ST minus K, comma 0, which generally occurs if, so this I can very well write it as the value is equal to ST minus K if ST is greater than K, and it is equal to 0 in the other cases. Correct? So what do we mean by ST greater than K? Probably I'll try to write it. ST greater than K, I can very well write it in this particular form, right? So when I am saying ST is greater than K, it is as good as, so let me go to the next step. I am writing ST is greater than K. What does that mean? I'll take it from here. ST is nothing but S naught into this. So that should be greater than K, right? So if I'm looking at that, S naught times e to the power of R minus Q minus sigma squared by 2 times T plus sigma root T Z. This entire thing should be greater than or equal to K. Again, a simplification now. E to the power of R minus Q minus sigma squared by 2 into T plus sigma root Tz is greater than or equal to K by S naught. And probably again, if I am taking out the E power, R minus Q minus sigma squared by 2 times T plus sigma root T times Z is greater than or equal to log K by S naught. Now from here I am establishing for Z. Z greater than or equal to log K by S naught minus R minus Q minus sigma squared by 2 times T divided by sigma root T. So the other way I can write Z greater than or equal to, I take out the minus out, I say log S naught by K plus R minus Q minus sigma squared by 2 times T divided by sigma root T, which is actually becoming Z greater than or equal to minus D2. Remember the Black-Scholes formula, D1 we said log S by K plus R plus sigma squared by 2 times T divided by sigma root T, and D2 we said D1 minus sigma root T. So that would have become log S by K minus of R plus sigma squared by 2 times T by sigma root T. So that's where we are getting minus D2, right? So Z greater than or equal to minus D2 is something that we are getting. So what does that mean? I can very well say now the price, so the call options the value is maximum of ST minus K. Now what is ST here? ST I can very well find out, which is S naught into e to the power of R minus Q minus sigma squared by 2 times T plus sigma root T does Z. This is st minus k comma 0, and this will come only when z is greater than or equal to minus d2. So what I can very well do now is, so once I know z, which is a standard normal equation, standard normal variable, so I can very well start finding out. I know that the density function for a standard normal variable is 1 by root 2 pi e power minus half x squared, and from there I can very well find out if I want z greater than or equal to minus d2. It's as good as taking the integral of z from d2 to infinite, e to the power 1 by root 2 pi e to the power of minus half x squared dx. But here the scenario comes is I want to integrate st minus k. So that's where I will take the same logic. This will continue 1 by root 2 pi minus d2 to infinite. So what is st? S naught into e to the power of r minus q minus sigma squared by 2 into t plus sigma root t into x minus k, because here I am taking x as z. With respect to z, I am doing this integration. So that's the reason I am taking this e to the power of minus half x square dx. And I need the present value, so I will take e to the power of minus rt. Now I will try to break these two terms separately, right? So the first term will become s naught by root 2 pi into integral of minus d2 to infinite e power minus rt, e power plus rt gets go off. So it becomes e power minus qt, e power minus qt, and this is becoming minus sigma squared by 2 into t plus sigma root t times x. This is what it is. Minus sigma squared by 2 into t plus sigma root t into x minus even multiplying this with minus x squared by 2. So it becomes minus x squared by 2. Minus x squared by 2. And this, the second term, I am taking it as k by root 2 pi e to the power of minus rt, right, e to the power of minus rt, and integral minus d2 to infinite e to the power of minus x square by 2 dx. So separately I am taking both of them. So here qt is a constant, so I can take it as s naught e to the power of minus qt divided by root 2 pi into e to the power of minus d2 to infinite. This I can very well write it as, I am taking out minus half. So sigma square t plus half sigma root t times x minus x squared by minus half plus x squared. So it is typically becoming x minus sigma root t whole square. Just write out x squared by 2 and minus 2x sigma root t, 2 by 2, so x sigma root t plus sigma squared t by 2. So I can write this something like this: dx e to the power of minus half x minus sigma root t whole square dx minus k by root 2 pi e to the power of minus rt, this minus d2 to infinite minus half x squared by 2 dx. Now, frankly speaking, this part, if you look at it, k 1 by root 2 pi 1 by root 2 pi into minus d2 to infinite minus half x squared, I can very well write it as k e power minus rt and d2, right? Because 1 minus d2 to infinite minus half x squared by 2, this entire thing is directly working out to n d2. Whereas what about this one? Now x minus sigma root t, I'll take it as y. So dx will become dy. But on the other side, because this minus d2 if I am looking at, so y will take the values from minus d2 minus sigma root t. Otherwise it is becoming minus of d2 plus sigma root t, which is becoming minus d1. So what could have very well happened is the first part s naught by root 2 pi e to the power of minus qt integrated between minus d1 to infinite e to the power of minus half y square dy. So this is again s naught into e power minus qt minus d1 to infinite is nothing but n of minus d1, right? Minus d1 to infinite is nothing but from our minus infinity to d1, both are one and same, so that's where I can very well write it as n of d1. So the first part is becoming s naught into e power minus qt n of d1. The second part is becoming k e power minus t n of d2. That is what is the typical formula for Black-Scholes equation, which is directly coming out for the pricing of the call option. So this is a mechanism that is typically engaged. Once I know the log normal model for evaluating the asset prices, wherein the relationship is logarithm of st by st1 is mu minus q minus sigma squared by 2 times t2 minus t1 plus sigma square root of t2 minus t1 times z. Once I have established that equation, I can solve the price of the call option or a put option, especially the European options, just by looking at their payoffs, finding out the expected value of the payoff, and then finding out the present value of the expected value of the payoff. So this is what is the typical mechanism to solve the equation and arrive at the Black-Scholes formula through a risk neutral evaluation model. All right.